way, you just pick both freely. And ready to go? Yes. So welcome to the second week, also for the people remotely connected. The first set of lectures is going to be by Jody and Cooley on plasmatic drug detection of classical winds.
All right, well, it's really a pleasure to be here in such a venue, and it's always wonderful to be working with students who are enthusiastic about the material. What I'm going to do is I'm going to start the lectures today by talking a little bit, sort of reviewing some of the things that I think you learned last week, so that you can see how things sort of connect into the winds. So if you see a few slides that are material you already have seen, don't worry, it's just to review it. And my vision is that today we'll talk a little bit about scattering rates, ideas like that, and then that tomorrow we'll talk a little bit more about experimental detectors. So today we'll think about the aspects that we think about as experimentalists when we try to build a detector, and tomorrow we'll move into specific detectors themselves. Yeah, I have to, how do I advance the slides?
God knows where this is coming from. I muted that.
And
but if you click the...
So I did that and I didn't get a slide forward. Yeah. There we go. Okay. So should I just continue or do you need to debug more?
I don't know what to debug. I mean, I can use.
Okay. So, so last week you learned that we have an abundance of evidence for dark matter. You, I think, learned about the missing mass problem. So from the dynamics of stars and galaxies and clusters, from rotation curves and gravitational lensing, and from simulations of the large structure of the universe, we all know that there's this problem that we can't really account for all the mass that is in the universe. And we also have a wealth of evidence that there's a particle solution, and that particle solution is maybe one of the most promising ways that we can solve this problem. So micro lensing techniques have mostly ruled out the idea of massive compact halo objects as being the dark matter. And if you go with a modified theory of gravity, although they can solve some of the issues, they seem not to be able to find a theory that can inclusively sort of cover all of the wealth of evidence that we have. And in particular, the CMB is very difficult, and as far as I know, has not yet been explained with a modified theory of gravity. We also have evidence that this dark matter should be non-baryonic in nature. This comes from the heights of the acoustic peaks, the power spectrum density fluctuations, and also forming the lightest elements in the early universe. And I believe you had probably studied these in depth last week with Anne Green. Okay, and then finally, the last piece of sort of evidence, or the last hint for us when we're trying to construct what dark matter might be, is that we know it still has to be around with us here today. So it has to be something that's stable, something that's neutral, something that's non-relativistic, which is kind of nice because it makes our calculations a bit easier. And we know for sure that it interacts with gravity, and we're hopeful that it also interacts with the weak force. And so when you take this wealth of evidence that we have, that you've learned about or will learn about in different lectures, and you put it all together, you get this really remarkable picture. And that is that our universe is made up of 26.8% dark matter. And so that makes a really interesting problem and an interesting particle for us to tackle as experimentalists. All right, so getting into the content, and I sort of already outlined this at the beginning of these lectures. So essentially, I think of it in sort of two different sort of categories. One is, how do we design a dark matter detector? In order to do that, we need to know something about the expected rates. We have to take into account background considerations. So backgrounds are particles or processes that might mimic a dark matter signature in our detectors. And then we have to think about the experimental signatures that we would go searching for. And then, like I said, tomorrow, I'm hoping that we will get into dark matter searches, whether that be in the morning lecture or it be in the evening when we have a little bit of extra time for discussion. If we go over, because we're talking throughout the lectures, we'll use that time to finish up. And so I want to answer in that sort of portion, have we already seen a signal? So some of you, I'm sure, probably all of you have heard of the Gamma Libra signal. So we'll talk a little bit about that. Then we're going to talk about detecting scattering from the nucleus using some existing experiments. So it's going to be a selection of experiments because I can't possibly cover everything that was out there. When I first started in this business, several decades ago, I could count on my hands and maybe borrowing my friend's hands, all of the dark matter experiments in the world. Now that's not possible. So I'm going to just pick some technologies and talk about them sort of in general and give you an idea of the types of experiments and hopefully give you the idea that this is a worldwide effort. Then I want to talk to you. So I know we're talking about classical WIMPs, but it turns out that when I started a decade ago, what we thought of as a WIMP and generally what we were searching for were very heavily massed sort of considered candidates. But now we actually can access lower mass WIMPs. So it is possible the WIMP could have a lower mass, maybe as low as a GeV or so. And so we're starting to now with technology be able to detect these lower masses by detecting single electron hole pairs using some current experiments. And this is really nice because it ties in with what Tang-Yan is going to be talking about later this week, which is the sub-GeV dark matter searches that work with sort of what we're going to call electron recoils. And if you don't know what that means, don't worry, we'll explain it in the lecture. And so I'm going to just slightly touch on how it is that we can get to sub-GeV using these experiments. But I'm going to continue to focus on nuclear recoils, which is what we do with classical WIMPs, where the electron recoiling signature is something that Tang-Yan will talk about. So basically, okay, sorry. So basically, if you think about dark matter and like detecting it and how you might do that, this is sort of the energy ranges that we can cover with direct detection experiments. And in this set of lectures, we're going to be focusing on the standard WIMP. Tang-Yan, as I said, is going to talk about this region more, but notice that there's this overlap region. So nothing, like when we talk about these categories, nothing is absolute with a border. There's always overlap going on between the different experiments. Okay. So we're going to start by considering detecting dark matter via nuclear scattering. Okay. So the idea here is that let's assume that the dark matter is not just interacting via gravity, but there's some other force out there through which it's interacting. And I'm not going to worry so much about what that force is, just that we can detect something that's not gravitational. And so the idea is that you have the elastic scattering. You have the elastic scattering of a WIMP. So you have a WIMP from our galactic halo coming in, hitting a target nucleus in the laboratory. You get an elastic collision, and from that elastic collision, the WIMP goes off in one direction, and then the nucleus that's left behind recoils at some angle theta r. And so basically, the idea is that this interaction here can occur via spin-dependent or spin-independent channels. And it turns out that there are other channels that this can occur through as well. And I'll briefly touch on that. And then in week 4, you're going to have a whole lecture about it. And we're going to need to be able to distinguish this type of event over all of the overwhelming number of background processes that can also occur in these detectors. So let's start by diving into the kinematics. Now, if you receive my lecture notes, which are a complete draft, you'll see that I have done this calculation out for you. They're both in the laboratory frame and the center of mass frame. For this lecture, we're just going to do it in the center of mass frame, but both reference points will get you the same answer. So you can calculate the recoil energy of the nucleus. We'll do this in the center of mass frame. So obviously, we're wanting to think about what's the initial momentum, what's your final momentum. So your initial momentum is going to be equal to the kinetic energy. And then your final momentum also has to be equal to the kinetic energy. So this is going to be the amount of the momentum transfer plus the reduced mass times the velocity of your dark matter particle. In this case, I'm using chi as the representative for our dark matter WIMP. So chi represents WIMP in this notation. So the reduced mass, in case you need a review of that, is just the mass of the WIMP times the mass of the nucleus divided by the mass of the WIMP plus the mass of the nucleus. Okay, so if we have elastic scattering in the center of mass frame, our initial momentum equals our final momentum. So that means that if I take my momentum transfer squared and I divide it by 2, that's going to be equal to 1/2 my initial momentum subtract my final momentum squared. And so just doing this out, writing this out, obviously, what will happen here is that you'll end up with a p squared and a p prime squared, but since p prime and p equal each other, right, your 2 cancels out. So you're left with p squared minus p dot p prime. And then you can write that in terms of a cosine of the cosine angle theta. So you have p squared minus 1 cosine theta. And then if I substitute in, then the reduced mass, so my momentum transfer, remember, is just mass times velocity because this is just non-relativistic. And I square that, I end up with my reduced mass squared times the velocity squared times 1 minus cosine theta. And here I kind of changed my notation a little bit. This theta here, I'm now explicitly going to call theta r for the recoil angle, which is this angle here, our recoiling nucleus. And just to be clear, this velocity v here is the mean width velocity that's relative to the target. So once you have this, you can then calculate the amount. Oh, sorry.
Oh, nice, thanks. I was just wondering, how much do the results of these calculations change if you're dealing with warm dark matter?
I am not exactly sure. I haven't ever done these calculations for warm dark matter, but if you have warm dark matter at some point, so warm dark matter is in that transition between relativistic and not relativistic regime. And so I'm not sure exactly how many corrections, like I'm not sure if you would treat that relativistically and then do this whole calculation using a relativistic framework versus a non-relativistic framework. Tracy, do you happen to know how they treat warm dark matter?
Unless I'm thinking about it wrong, I just think that like warm dark matter is supposed to really receive when it freezes out.
Okay.
It's restricted a lot since then. So I guess warm dark matter today is probably pretty non-relativistic.
Okay.
And I mean it has to be done to our galaxy, say in the galaxy at all. So the input for warm dark matter velocity is not super different, and you can still make these non-relativistic approximations.
And I'm going to repeat that. I'm going to truncate it and repeat it so that people offline can say. So Tracy, who's worked more in this sort of regime, indicated that she thinks that because of freeze out arguments and then it being gravitationally bound today, that means that essentially you would probably treat warm dark matter in a classical sense and that the resulting spectrum in your results would be very similar to what you'd have in the non-classical case.
Okay, thank you.
No problem. All right, so this is our recoil energy. So it's our momentum transfer squared divided by 2 times the mass of our nucleus. Okay, so, and then here I just wrote it out in another form where I just took the Q. And then what I'm going to do is, up in this corner, a lot of times I like to keep up in the corner equations from the previous slide that we might use again on the existing slide, just so you understand the way my notation works. So next, what we're interested in is, what is the minimum dark matter particle velocity for which we can actually expect to get a recoiling nucleus, right? So you're going to have to impart some amount of momentum to do this. And in that case, right, it's going to correspond to the case where our cosine theta is equal to -1. And so just putting this in and calculating it out, we can write this as, so the ER, so our recoiling energy is the reduced mass squared times the velocity squared divided by the mass of our nucleus. times 1 minus 1, which is 2. And then if I rearrange my terms, I can find an expression for the minimum velocity. And it's the square root of the mass of the nucleus times our recoiling energy divided by 2 times the reduced mass squared. And that whole thing, we take the square root of. All right, and so I'm just circling that. Okay, so this has a few implications. Okay, the first one is that lighter mass dark matter particles, so if the mass of our dark matter is much less than the mass of our nucleus, must have larger threshold velocities. So the lighter your dark matter, the faster it needs to be moving in order for us to register something in the detector that we can actually measure. The second thing that I want to point out, so I'm not really going to be talking about inelastic scattering at all in these lectures, but clearly you could also do a similar type of calculation for inelastic scattering. And if you do that, what you would find is that that can further increase the minimal velocity that would be needed in order to register something in your detector. We also then want to think about the average momentum transfer that you have in elastic scattering between a WIMP and a nucleus, right? So this momentum transfer is going to tell us something about like what is the energy scale that we're measuring or trying to measure in the detectors. So here I'm going to just consider the case of a 10 GeV WIMP whose speed is 100 kilometers per second. And so again, like this is just non-relativistic kinematics. So our momentum in that case can be just written out as the mass times the velocity, doing some unit conversions. We find that means that we need about 3 MeV per C of momentum transfer if the dark matter is 10 GeV. If I were then instead to have 100 GeV dark matter particle, then the momentum transfer essentially is just a factor of 10 bigger. And then we're talking about 30 MeV per C, the momentum transfer that we need. All right. And so one other thing that's kind of interesting to consider when you're thinking about this is what's the de Broglie wavelength that corresponds to this momentum transfer. So let's just say we're looking for approximately a 10 MeV per C squared, per C momentum transfer. So the de Broglie wavelength is just HC times PC or divided by PC, as you know. So if I throw some of those numbers in, I always like the unit HC because it has this really memorable number that you can use again and again and again. Divide it times PC, you find that this is about 12 picometers. Why is this interesting? Whoops, sorry. This is interesting because this 12 picometers is much greater than the size of most nuclei. So the size of most nuclei goes as R0 8 to 1/3. So what this means is that the elastic scattering amplitude on an individual nuclei will add coherently. So this, you sometimes hear this factor, this A squared coupling that we get, or this A squared enhancement, comes from just thinking about the de Broglie wavelength. Oops. Okay, so I want to start by doing sort of a rough back of the envelope. Oh, sorry, yes, back there.
Just a question on the elastics and inelastic. So
Yeah.
is it enough to assume elastic scattering if you have this big difference between the wavelength of the incoming particle and the nucleus, or is there no assumption we should make about why it has to be elastic?
I think, yeah. So the question was, what assumptions do you have to make in order for it to be elastic versus inelastic scattering? And I think the answer is that you can get elastic or inelastic scattering in either case. Why elastic scattering is more favorable than inelastic scattering can have to do with this argument you're saying as far as like the pinpoint versus the size of the nucleus, but that doesn't necessarily mean that you can't find a way to make inelastic scattering work as well.
This really refers to like the loss of particles. So if it's coming in, it makes the particle inelastic.
Yeah.
The size of one.
Okay, no problem. So let's start with just something, a simplified event rate in a detector. And then, okay, yes, sorry. I don't see the hand very well.
Yeah, no, so I was just wondering since, I mean, we're considering here that the particles are free, but in practice, the like nucleus scattered by the wind would be found in crystal or something like that.
Right, yeah, we're gonna get, okay, so, okay, go ahead. No, you might, do you have more to your question?
Yeah, no, I was just wondering how that's gonna change, like results, like the minimum velocity
Yeah.
necessary for the
Okay.
scattering to occur.
So the question was, is that, so your nucleus is going to be bound, and will that essentially change your results, for the minimum velocity needed? Because in this case, we were just considering them individual. The answer is that perhaps, on a small level, it might change things, but really, what we're going to do is what we want to do is we want to get into this rate calculation. And what you're going to do is what you're going to see is that in doing the rate calculation, there actually is a lot that we need to take into account when it comes to both particle physics, astrophysics, and nuclear physics. And we're going to get into that in like 5 minutes. So we're going to start with this simplified model here. I'm just doing sort of simplified model. And then what I'm going to do is I'm going to step back and say, okay, what's going on in reality, taking the case that, we do have these nuclear form factors and various things that we need to take into account, and how does that change the results, and how does that change our structure? So if you wait maybe 5 minutes or so, perhaps you'll get a more satisfactory answer. All right, so the differential rate for a very simplified WIMP interaction. So again, this is simplified. You have a stationary detector in the galaxy. This rate is given by d by dr, where r here is the event rate, divided by dE sub r, which is the recoil energy. And I realize now that this was a terrible notation choice, but hopefully you'll understand by context. And this is equal to the total event rate r naught divided by E naught times little r. E here is the most probable incident energy. And in sort of a simplified model, this we just take as a Maxwell-Boltzmann distribution. R is this kinematic factor, 4 times the mass of the dark matter particle times the nucleus, divided by the mass of the dark matter particle plus the mass of the nucleus squared. And that's all taken to an exponential, E to the sub r divided by E naught times your kinematic factor. Okay, and so when you take a look at this, basically what this means is that if I put on a log, not log plot, the differential rate with respect to recoiling energy, I have this exponential function that's, is featureless, right? It's just an exponential function that you're looking at. And so if I want the total event rate, then I just integrate this expression. And when I do that, I get R naught. And in this case, then the mean recoil energy, so if I take the mean of the recoil energy, this I just integrate from 0 to infinity, the recoil energy times dr dE, and this is an element dE of the recoil energy. That gives me E naught times my kinematic factor R. All right, so in this very simplified model, let's think about what this would mean for nuclear recoil energy that would be detected or deposited in a detector. So again, I'm going to just start with this canonical 100 GeV WIMP that we have. And I'm going to say, let's assume that we have a detector that's nucleus size is similar in size to the WIMP, so that they're both 100 GeV. So our formula is that the mean recoiling energy is just E naught times R. Okay, so E naught, because this again, non-relativistic, so we can just use kinetic energy, 1/2 the mass of a dark matter particle times its velocity squared, and then our kinematic factor. And of course, in our case, you can see why I picked 100, because that makes our kinematic factor a nice 1, which is easy to go with. So assuming that our halo is stationary, that means that the mean WIMP velocity relative to the target is approximately 200 kilometers per second. And so if we substitute this then into our equation, right? So it's just a 100 GeV times, I wrote this here in terms of C, 0.75 times 10 to the minus 3C, that quantity squared divided by 2. And this, if you calculate it out, will give you something around 30 keV. All right. So that's great. So 30 keV, simplified back of the envelope calculation. But let's get into the details. Like the gentleman in the back said, you know, it's not like there's a lot going on when you talk about a particle interacting with a nucleus in a crystal. I saw your hand up.
Yeah, sorry, the blue slide.
Yes.
What do we mean by the halo? We assume the halo
Ah.
is stationary. That it doesn't have a like,
Right,
open motion?
So this is just this is like you pick a reference frame. And I'm picking a reference frame where the halo is stationary and we're moving through the halo.
Right.
You could also pick a reference frame where we're stationary and the halo is moving around us. You could pick something in between. I just picked this because it made the calculation simple. But you can always choose your reference frame. And I always encourage my students to choose the reference frame that makes their calculations as easy as possible, unless there's a good reason not to do that. Yes.
Where does like the exponential decay come from in that equation? In the previous slide?
In the previous slide,
Yeah.
sorry.
It's just like the rate formula. Where does it come
Yeah, this is just so the dark matter, the rate of the dark matter isn't necessarily, I mean, going to be, or sorry, it's okay, so when we're thinking about the event rate, right? It's not necessarily that the event rate is just going to be a number. There are dependencies on the event rate that cause it to be exponential. And so this is just something, you know, that's chosen. When I go into more detail, like let's move on to like the more realistic simulation. I think you'll start to see where some of this falls out. And if not, we can come back to it. So let's actually start picking up the details. So I just picked a model, okay, and said, let's see what this model gives us. But let's start thinking about like, why is it that you might pick that as your model? So in my model, I didn't talk anything about the interaction. I didn't talk anything about like what the halo, what the distribution of dark matter was. I didn't talk about any of these details. Let's now take our simplified model and let's fill in the details. So we need to take into account sort of the following things. The first is that the dark matter will have a certain velocity distribution. Okay, and so that velocity distribution may modify what our event rate is. The dark matter detector is on Earth, and the Earth moves around the sun, and the sun moves around the center of the galaxy. So this is something else that we need to think about and take into account when we're trying to come up with the event rate. The cross section itself depends upon the spin interaction. So that means like the interaction with the nucleus would have some spin, and there could be, you know, some interaction that's going on there. And so in the simplest case, this is either spin dependent or spin independent. The simplest case is actually spin independent. The dark matter scatters on nuclei, and nuclei have a finite size. And since the nuclei has a finite size, we have to consider form factor corrections, which are different for spin independent and spin dependent interactions. We also have to realize that the recoil energy is not necessarily the observed energy. So the detection efficiency in real life isn't 100%. And finally, the detectors have a certain energy resolution and a certain energy threshold. So all of these factors we have to take into account when we're thinking about what's the real situation in a dark matter detector. So let's start with the master dark matter formula, okay? So the number of particles detected, I'm going to call that N, big N, is the dark matter flux times the effective area of the target multiplied by the observation time. So we have the number of particles detected, the observation time, the density, the velocity, the number of targets, and our cross section. Yes.
So it seems like in the things that we're taking into account, we're really only looking at the kinematics. We don't really care about what kind of interaction might be going on. We're just assuming it's billiard balls.
We're assuming elastic collisions.
Okay.
And this is going to be an elastic collision. So all of this assumes an elastic interaction with the nucleus.
Okay.
It is true, it could be inelastic but in that case, okay, so in that case, we're not going to cover it, but if you're interested in that, I can point you to some papers that talk about how you would do the calculations out to come to rates for inelastic collisions. So there was a time when inelastic scattering dark matter was sort of topical and popular. And my recollection is that it was Neil Weiner from New York University, who was really big into this and had published several papers on it. And I know that our collaboration, and I think the Xenon collaboration too, had actually done the interpretation of inelastic scattering dark matter in their detectors. And so to give you an idea just of how this works, right? Because in an inelastic collision, you don't have energy is always conserved, but you don't have the conservation of energy principle that you can easily fall back on, because you lose some energy in the collision essentially. And so my recollection is that essentially normally we're looking in our detectors at that time between recoiling nuclei that were between sort of 10 and 100 GeV. But when we were looking for an elastic dark matter, we were looking up to 500, I'm sorry, not GeV, KeV. We were looking up to 500 KeV of nuclear recoiling energies. So it's sort of a factor of 5 higher that your thresholds, you could kind of move. So they certainly were a type of dark matter that people looked at one time. In the end, when it comes to a detector itself, right? Essentially, we look to theorists who are developing models that are reasonable and seem plausible. And then we're taking our data and interpreting what does that mean with this data? What can we say about it? So that always is that in this field, there's sort of this marriage, if you will, between what experimentalists are doing and what theorists are doing that help drive things. And so this is what I can tell you. I'm going with the elastics case. It's really nice. I think Tracy has something she'd like to say.
I'll just say a brief comment on this. So I guess there's at least two kinds of inelasticity, right? That's where the inelasticity is on the standard model side, where you're exciting some kind of vibrational state in the nucleus or something, or where the inelasticity is on the dark matter side, where the dark matter has some internal structure and you're exciting that internal structure. And the case that Jody is talking about is the second state, where the dark matter has an excited state, and you incite that excited state as opposed to scattering. And that, as Jody says, what happens then is that instead of having this exponential fall spectrum, you have a low energy cutoff, so you have no events below some energy, and the events cut off. That's not high energy. It basically, because every recoil is going to get some energy from the inelasticity. So, but I think, I suspect that Tanya, when she talks about the low mass dark matter, maybe talking about some stuff that is, that has been non-trivial interaction on the standard model side. Because the very low mass dark matter, you can get stuff like absorption of dark matter and binding of dark matter. So yeah, this is and I think but it's good to understand that elastic scattering cycle.
So elastic scattering, I think the reason that we always still go back to this is because it's a very straightforward, looking at Occam's razor. But certainly, what Tracy said. Okay, so I probably can't repeat this word for word, but I'll try to summarize it, and then Tracy, let me know if I let something out important. So this is a question about inelastic scattering dark matter. And so Tracy pointed out very rightly that there are two sort of different ways that you can have inelastic interactions happening. One is that the nucleus itself gets into an excited state that oscillates. And the second is that the dark matter gets into an excited state and it can oscillate. And what I was talking about, the work that Neil had done, was the former case, where the dark matter is excited and oscillates. I'm sorry if I forgot something else. I might be able to, I think that's the primary thing. And then, I remember. And then going on to that, so that's why, essentially at lower kinematics, there's sort of a truncation. You don't get these lower nuclear recoils. But you can get other sorts of interactions that can happen, like absorption. And so if you go back to think about sort of an earlier slide where I had the spectrum of how it is we can directly detect dark matter. And so I said, this lecture is going to concentrate on this small window, which is the WIMPs, which we often think of in an elastic scattering case. But there's lots of other interactions that could happen that we look for. And we're really fortunate, you're super fortunate, that we are in an era now where we can actually have not just like the ideas of this lighter mass dark matter, and we can explore like what are the implications of having these different types of interactions, but we now have technology that we're developing to actually be able to measure it. And so to me, this is like a whole new sort of golden age for dark matter. I think, you know, what Tangyan is going to talk about is kind of amazing because we can do the types of dark matter searches for things like absorption or electron scattering, sometimes with very small detectors. These WIMPs that we're looking for here, we need massive detectors to continue to make progress looking for them in the regimes we are now. And so I think this is very exciting because our toolkit for being able to tackle this problem is so much bigger. I mean, when I was starting as a postdoc, we were like, you know, its interaction essentially had to be like, we had to have like 10 keV of nuclear recoil or 20 keV of nuclear recoil in our detector, or else we didn't know what to do with it because there was just so much noise and crap we couldn't deal with. And so it's really very exciting what the experiments are doing now. So I have to say, I think this is a great time to be working in this field. Let's see, so I think I went through this, yeah.
If I can add something to the inelastic discussion, there is a priori no reason to believe that the scattering is inelastic. It was a hookup model for the gamma signal, where the splitting between the pseudo matter states is on the keV range. But yeah, this can happen, for example, if you have an SU2 that is spontaneously broken, you can have a mass splitting of that range. But if the mass splitting is larger, then you cannot see that with nuclear recoils.
Yeah.
So elastic scattering, I believe, is a very good assumption.
Yeah. So just a repeat of why it is with even in inelastic scattering, the difficulties you would have with direct detection of a nuclear recoil, and why then that makes elastic scattering a good place to start for those who are online. All right, so going back to our basic formula, I mean, this is like the most basic formula you can write down. And so what we're clearly going to do is develop each component of this. So we're going to need to determine the spectrum of dark matter recoils. So this is the energy dependence of the number of detected dark matter particles. And so this we're going to write then is the derivative of the number with respect to the recoiling energy is equal to the time times the number density times velocity times the number of targets we have times our cross section as a function of recoiling energy, d sigma dEr. Okay. So we're also going to need to consider dark matter particles are described by their local velocity distribution. So this is f sub v, where v is the dark matter velocity in the reference frame of the detector. The lectures, I think, on dark matter density distributions, is Annika going to cover that? Or did you have that last week? A little of both, okay. Okay, good. Okay, so this is, so this basically then means that we can rewrite our formula, our basic formula that we had there now is dNER is T times N times our number of targets. Okay, we're going to integrate over this minimum velocity, just recalling that this is the minimum velocity that we've already defined. So this is going to be equal to the velocity times this function f sub sf, which is a function of velocity, is sigma dr times dv. And so I want to sort of then take a note of the following. So remember, this is our number density. Yes.
Sorry, this minimum velocity wasn't this in the similar mass frame, so don't we need to do some kind of Galilean transformation?
No, I think we're okay here still.
Okay.
Yeah. So our number density is equal to the density divided by the mass of the dark matter particle. The number of targets is the total mass of our target. So this would be like, say, the mass of your crystal or the mass of your target divided by the number of nucleons. And this E here, this is essentially the lifetime of the detector, or the lifetime of your exposure is the times the time that you run your experiment times the mass of your target. So if I make substitutions of these substitutions into our master formula, we can rewrite our master formula then just as our exposure times the density divided by the mass of our dark matter particle times the mass of our nucleus. We're integrating this over the minimum velocity, and that gives us, and the function, of course, that we're integrating is still V times our density distribution times the derivative with respect to the recoil energy of our cross section. Yes.
Is that rho a time-dependent quantity as we move around the galaxy?
So I'm gonna, okay, so the answer is, in reality, nobody knows. So we're gonna say like that the density, because this is the density in the area that you're moving through. And clearly the structure of the dark matter halo, has structure. But generally speaking, we're going to talk about what this dark matter distribution sort of looks like, or in a simplified model. But we basically take a model that's isothermal, isotropic. And so in that case, then this density here is not stationary. It doesn't change with motion or anything. So in reality, maybe, probably, who knows? For our purposes, we're taking a model. If we ever figure out what it really is, we can incorporate it.
Okay, thank you.
But that's an excellent question. So you see, there's a lot of things that are reality that we don't know, but we try to take a model that we can do something with. Yes.
Is there also kind of a maximum velocity in this distribution?
A maximum velocity. Okay, so the question is there a maximum velocity that the dark matter can have?
Or
that-
at least the distribution takes only works from like kind of a-
Yeah. So there is a district. Okay, so let me say this. We're going to talk a little bit in a future slide, a little bit more about like the type of simplified model for the dark matter distribution that we take when we do these calculations. There certainly is a maximum velocity that the dark matter can have where it doesn't go flying off into outer space. So there is this, it's called the escape velocity. And my recollection is that we typically use something, I think is 650 kilometers per second. And so what will happen is when we look at the dark matter distribution, there's a truncation, or the velocity distribution. There's a truncation at the end where it follows some spectrum and then it's truncated at the escape velocity. So that's a great question. Any others? Excellent. Okay. Let's see. So we've gotten through this. All right. So now what we really want to know is we want to, and when we as experimentalists are thinking about this, what we're really thinking about is the differential event rate. Okay. So that is an expression that's in events per keV per kilogram per day. All right. So what we start with here then is we have the event rate as a function of recoil energy is equal to rho naught mn mx, so the mass of the nucleus, mass of our dark matter particle, by all this stuff. Okay, and so we have the local wind density that we're using here. So if we're now taking the formula we had and we're transposing it into something that we think about going. The nucleus mass, I already said the WIMP mass, the WIMP nucleon cross section. This F sub V here, this is essentially the WIMP speed distribution in the detector frame. And always looking at the minimum WIMP velocity, which can cause the recoil. We always care about that. And so what you can see from this, and so now we've taken our very simpler master formula, is that when our event rate needs input from astrophysics, it needs input from particle physics, it needs input from nuclear physics. And so we'll start looking at each of these independently. And then just as a summary here, remember, we're still talking about elastic scattering. This happens in the non-relativistic case in the lab frame. can be written as this formula. So these are all formulas we already have and we've talked about, but I just wanted to, kind of regroup as we move to the next section where we start looking at some of the particle physics and astrophysics and nuclear physics. Yes.
When we say this is measured in units of events per EV per kilogram per day, the kilogram is kilogram of the
It-
target.
Yes.
Okay.
Yeah, exactly. And you can imagine, like, we want to do that because if we're thinking about, otherwise, if we're comparing detectors that have different size targets, right? Yeah, you can make your detector look better just by having a bigger target than somebody else's detector. So thinking about it per kilogram normalizes it for the community. All right, so let's start looking at each of these elements individually. So let's start with this here. Let's start with this cross-section element. Sorry about. Okay. I feel like I have just done the same slide over again. We're going to take a look at that element. I think something happened funny with that transition. So the event rate is happen. So if we want to know the event rate, right, what we're going to do is we're going to integrate that expression over our threshold energy to infinity. And so when we integrate this out, we end up with dEdr, rho, our dark matter density times the mass of our nucleus, mass of our dark matter candidate. And then we're still looking to integrate over the velocity of the dark matter particle, v sub f, d sigma, dEdr. Okay, so the scattering cross-section takes place in this non-relativistic limit. And since it's taking place in the non-relativistic limit, that means that we can approximate it as being isotropic. So what that means is that d sigma over d cosine theta is a constant and can be written as sigma divided by 2. And so, so if you recall, our maximum recoiling energy we had found to be 2 times our reduced mass squared times velocity squared divided by the mass of the nucleus. So that means that we can write our recoiling energy as in terms of the maximum recoiling energy times 1 plus cosine theta divided by 2. And so so that gives us, so that means that if I take the derivative of our recoiling energy with respect to cosine theta, that's just going to be equal to E max divided by 2. So from that then, we can write this d sigma DER element as d sigma of d cosine theta. So the derivative of our cross section with respect to cosine theta times the derivative of cosine theta with respect to ER. So this is just using the chain rule. And so we can write this then as sigma divided by 2 times 2 over ER max. And that just gives us our cross section divided by the maximum recoiling energy. And then if I substitute in E max, our expression for E max, and we write it in terms of the reduced mass and the velocity. Okay, so with that expression in hand, we also want to recall that the momentum transfer for the non-relativistic processes can neglect the kinetic energy of the nucleus. So what that means is that our momentum transfer is equal to the square root of 2 times the mass of the nucleus times our recoiling energy. And that expression is on the MeV scale. And we remember that the de Broglie length that we were looking at was on the femtometer scale. Oh, sorry. So what that means is it means something for the light nuclei. So what this means is that if the nuclei is really light, your dark matter particle sees the nucleus as a whole without any substructure, right? And this is great for simplifying our calculation. But if you have a heavy nuclei, that would require the inclusion of nuclear form factors in order to count for the loss of coherence. So if our dark matter particle is light enough, we can have that coherence, but if not, we have to think about these form factors. And so this WIMP nucleon cross-section can be separated into a spin-independent component and a spin-dependent component. So the spin-independent component comes from scalar or vector couplings to the quarks, and the spin-dependent term arises from the axial vector couplings to the quarks. Okay.
Why are we talking about coupling the quarks? I mean, haven't we been looking at with regards to the entire nucleus?
Right, now I'm saying, okay, well, what if that assumption wasn't good enough? What if we actually do need to take into account the substructure of the nucleus?
Okay.
How do we do that? Sorry if I wasn't being clear. So if the nucleus, so if your dark matter is light enough, yes, and hit something, yes, indeed, you know, the spin independent will dominate, but it may be that your dark matter happens to be of a certain mass, or it happens to really care about these spin dependent couplings, or maybe you want to make those corrections. How do we account for those?
Okay.
So this might be that it is just spin independent and you ignore the spin dependent coupling, or it may be that it's spin dependent. Like that's typically the cases that you look at one or the other. But I just wanted to show, like, where does that come in? It comes in here, or it's one place where it comes in. And this actually becomes more complicated in the next step too, as we start digging down. So we start with the simplest case and we keep adding more and more structure to make our calculation more and more detailed. Yes.
I'll wait for my question for the next slide.
Oh.
See if it gets answered.
Okay. So to calculate this, you can add coherently. So these functions then can get further broken down into their spin and scalar components. So you can see here we have the mass of the nucleus over 2 times the reduced mass squared times the velocity squared. And then you have the cross section, the spin independent cross section, the spin dependent cross section. This is particle theory. And then you have the nuclear structure that you take into account. These are called form factors. So that's your nuclear structure. And so the form factors are taking into account any dependence you might have on the momentum transfer. So, all right, so we're up here still. This is the master formula that we had looked at from, our master formula keeps getting more and more complicated, but we're just looking at this one term from the master formula that we've written like this. And so what I'm going to do is I'm going to take the form factors and I'm going to take the cross sections and I'm going to look at them each independently. So let's start with the form factors. So essentially you can think of the form factors as encompassing or incorporating, maybe not encompassing, but incorporating the quantum mechanics of your nuclear interactions. And so now you probably have a whole lecture on form factors. Okay, so the form factor that I'm going to pick here just as an illustration is one of the form factors that's used most commonly. It's the Wood-Saxon's form factor. But like there are people who research this and this gets used not just, I mean, like this is nuclear physics theory to some extent. But there are people who work in particle theory who worry about this stuff too. So for spin-independent interactions, a very commonly used form factor is the Wood-Saxon form factor. It looks like this. So the form factor, which is a function of the momentum transfer, is equal to 3 times the first Bessel function, which is a function of the momentum transfer times the effective radius of your nucleus, divided by your momentum times your effective radius, that quantity squared, times the exponent q squared, s squared divided by 2, where s is something called the nuclear skin thickness. And basically, what I would say about the nuclear skin thickness is that it's approximately equal to a femtometer. Okay, and so this is the form factor. And if you work in form factors, and you take a look at this form factor, if I take the form factor squared and I plot it as a function of recoil energy for different targets, you can see that you get different shapes. Like you actually get points where it goes to 0, and that has to do with the fact that from this formula here, and I see your hand, you have the momentum. It's dependent on both the momentum transfer and the effective nuclear radius. And so from there, you get these structures within the form factor itself, depending on the size of the nucleus. And so what you can see here is you're going from lighter to heavier nucleus. And as you look at the heavier nuclei, you see that structure more prominently. You would start to see the structure probably in these lighter nuclei if you went out to higher and higher recoil energy. Yes.
Thanks. I'm having trouble understanding just qualitatively what the form factor is.
So essentially, it is the I mean, I don't know how to. Let me think if I can try to think of a better way to explain it. But essentially, it is the quantum mechanics that's going into effect. I mean, like a nucleon is like a real nucleus is not just like a point particle, right? It has structure. And so essentially, I think the form factor is kind of taking into account the interaction that you're getting with that nucleus and the fact that that nucleus has some structure to it. So I think that might be, I don't know that I can think of like an analogy or something to give you a clearer mind, but I see other hands, so maybe somebody else has an idea. But essentially, because the nucleus isn't a point, and if you start treating the subtleties of the substructure within, then there are sort of like corrections that you take into account. This work, a lot of this work is kind of like it's very computational, right?
So just to follow up.
Yeah.
So larger nuclei have more complicated form factors because there's more substructures. So
Well,
the
okay.
form factor is kind of encoding.
The form factor is the same,
Okay.
but when you plug in these different quantities for heavier nuclei, you see the substructure at lower energies. And yeah, right? This is so like tungsten, right? We can see it here. But if you go to xenon and iodine, you see this. You go to germanium, here you're getting this exponential here, and you can imagine at higher energies it would fall off as well, right? But so it kind of scales it in this Wood-Saxon form factor, right? Because, and so the reason is because the mass of your target, so if you remember, you have to think back to the momentum transfer, right? The momentum transfer, remember, has something to do with the size of your incoming particle and the size of the nucleus. The heavier your nucleus, the less momentum transfer you have. And so you're seeing, because this has an exponential dependency, this exponential gets pushed out further and further for lighter targets where you're having more momentum transfer for the same mass particle, right? Does that?
Yeah, that helps. Thank you.
So yeah, so in a sense, all of these are, right, just, it kind of has the same, it has the same sort of general features, but the features happen at different recoil energy scales, depending on the momentum transfer and the effective radius. It's a combination of both.
I can maybe add that this form factor is taken from electron-proton scattering. So you are effectively assuming that the weak scatters are distributed as the charge in the nucleus, I think.
Yeah. So for those that are online, I don't know your name. I'm sorry, I don't have. Okay, Rafa. Okay. Yeah. Okay. That this form factor here comes from electron-proton scattering.
I think.
He thinks, and I don't recall. I have to be honest. Yeah.
I wanted to ask if this is like similar to the part of distribution functions.
Oh, say it again.
Like, for
I couldn't hear. Sorry.
It sounds similar to quantum distribution functions in theory, but I'm not sure.
Okay.
if it's
So, yeah, so one of the students in the audience whose name
Adriana.
Adriana, okay, and I'm sorry, I'm having a hard time hearing people, said that this reminds her a lot of the proton or the parton distribution functions that you have in quantum chromodynamics, QCD. I don't know for sure. I'm not very much an expert in parton function distributions. I know I should be because at my school we have a bunch of theorists who are really into them, but I don't know.
I guess, okay, yeah, but I think it's a similar idea, right? Like you have to tell me about the whole thing and then I play on. This is, it's like I looked up the word sex potential is this is just like the Fourier transform the models that are attached information inside the split based on the program.
And so, and Tracy, for those online, basically says she agrees that it does have a lot of similarities. All right, so so we did spin independent. Now let's move on to spin dependent. Okay, so in spin dependent interactions, the form factor goes as this function S as a function of ER over S naught. And so what does that all mean? Okay, so S as a function of the recoil energy is equal to this A naught times S00 ER plus A1 squared S11 ER plus A naught or A0 A1 2S01 of ER. Okay, so these S's here are isoscalar or isovector. So isoscalar, isovector, and interference form factors. And these A's are the isoscalar, isovector, and interference couplings that you have here. So A naught is equal to A for the proton plus A for a neutron. And A1 is A for the proton minus A for the neutron. So, all right, so we got the form factors out of the way. Now it's time to take a look at our cross sections in both spin independent and spin dependent. So the cross section for spin independent is equal to 4 times the reduced mass squared divided by pi times z times f of p plus a minus z times f of n. Now in this case, let me just do this out. This case, these little f's, they're not form factors. Okay, this is a new concept. This is basically a coupling. It's the coupling to the proton and the coupling to the neutron. And for those who are more interested in the exact one, this is the scalar for fermion coupling constants. So they're a little bit like fermion coupling constants, but they're specialized more for the proton coupling and the neutron coupling. And in most models, F sub n and F sub p for the neutron and the proton, they're similar in magnitude. So the scattering, because that happens, the scattering then adds coherently with A squared, and that's where you get your A squared enhancement. Because these two terms are essentially the same. Yes.
Do any of these quantities change based on our dark matter model, like whether it's a scalar or a?
Yes. So I mean, right. So if you, depending on what your dark matter model is, it may be that your spin independent or your spin dependent coupling like becomes more dominant and becomes the interpretation that you make. And so what you'll see in dark matter experiments, like if you read papers from any of the experiments releasing results, some of them are often quoting their results in terms of spin independent interactions. And some of them are quoting the results in spin dependent interactions. And again, that depends on the model that you're taking. And again, part of it is because we don't quite know what the dark matter is. And even if we know what it is, we don't know exactly like the nuclear and particle physics that goes into it, like which of these terms would be most important, right? And so after we get through this, and I want to point out just as an illustration that like I'm going with spin independent, spin dependent here. I haven't even added in the fact that those are just taking 2 of the simplest models. Really, there's a whole effective field theory that you could take into account where it could be much more complicated. you're in week 4 going to have lectures from somebody who really understands the quantum field theory and how it relates to dark matter. But I want to illustrate here for you, just showing you a few slides after we get through these simplified models, like what does it mean if you add more complexity in, and why might we want to think about more complexity in terms of like quantum field theories? But yeah, so, all right. All right, so spin dependent. Sorry. Okay, so in the spin dependent case, then you end up with something that relies on scales as the Fermi constant, the reduced mass, times a term that involves the nuclear angular momentum. And then also you are still considering the coupling constants to both the proton and the neutron. And then these new terms, S sub p and S sub n, these are the expectation values of the proton or neutron spin. Yes.
So since I see this Fermi constant here, are we assuming some kind of weak interaction model with some kind of W boson?
So this is certainly a weak interaction that's happening. So this framework that we're doing here is in terms of if the dark matter particle is a weakly interacting massive particle.
So when you say weakly interacting, you don't just mean it has a small coupling, you mean specifically weakly interacting, weak force.
Yeah, we interacting with a weak force, So in this case, what you can see here is that this now your scattering cross section is scaling with the spin of the nucleus, right? And you don't have a coherent effect in this case. So here you had a coherent effect that came in because in most of the models that you have, these factors F sub n and F sub p are similar. But here, that's not necessarily the case. And so generally, if you're looking for a spin dependent, an interaction that is happening where spin dependency is sort of the dominant contribution, you want to look for a target that has a free neutron or a free proton for the coupling to happen to. So essentially what you do is you choose your material in the spin dependent case, if that's really what you want to go for, where you have that. And so this table here, which also will be in your lecture notes, gives a variety of targets that people have thought about, and gives their atomic number. You have the odd nucleon for each of those, the spin, and then your expectation values for neutron and proton. And then really what matters is sort of, this is just another scaling factor that's used to compare different targets for favorability. And you want to find one that has a good value. So in this case, you know, things like fluorine are used in like bubble chamber experiments. Iodine's another one that people have considered and looked at. And xenon, of course, is another target that has favorable characteristics for going after spin-dependent interactions. All right, so now as I talked about, so the next thing sort of thinking that we think about a little bit is thinking about the model that you would have for your halo. And so this is the idea, and I think I had already said this at one point, but yes.
The dependence of the dark matter model resides only in the constants that you have there.
Oh, in this case, that was okay. So the question is the let me go back a slide, maybe, or maybe not. Okay, so the question was, if I remember right. So in this case here, sorry, can you repeat your question?
Dependence to the dark matter model, like she asked.
Yeah.
It's a scalar or a fermion.
Yeah.
Or vector.
Okay. Yeah. So in this case here, in the spin dependent case, the coupling is happening to either a proton or a neutron in the nucleus. So in this case, when you have the interaction, you can kind of think of it as that the WIMP, when it comes in and it's scattering, does suddenly care about, you know, the structure of the target and the protons and the neutrons, and is either more favorably interacting with a neutron or maybe more favorably interacting with a proton for whatever reason. Like this is the nuclear substructure of it. So in the spin-dependent case, the interaction is such that the coupling to a proton or a neutron is important. It's not that the terms are similar. The spin-independent case, you can think of it, the way I think of it is, in the spin-independent case, the particle, the WIMP comes in, it doesn't care. It just sees the nucleus as kind of a point and scatters. And that's, let me go back here, one more slide if I can. And that's shown by, okay. And that's shown, and the reason for that, so it comes in, because these terms here, these couplings to the proton and the neutron are sort of equivalent and similar, that's why you get the A squared enhancement. The particle, the WIMP, doesn't care. In this case here, these terms are not similar. And so there is concern that you have to take in the coupling to the neutron and the coupling to the proton. So in this case, you don't get an A squared enhancement. In this case, if you're looking for spin independent sort of interactions, you want to go with a heavier target or a target that's similar in size to what you think your dark matter particle is to make the most of the A squared enhancement. In this case, you don't get that enhancement from the size of the nucleus. You get your largest sensitivity coming from having a free proton or a free neutron that your dark matter particle can couple to. That might be the most straightforward way to say it. Other questions? Yes.
So is another way of saying it that kind of neutrons in a structure get shielded somehow? That's why it's
Yes, actually, that is actually if you were using, so the question was, as another way that you can say this is that like a proton or a neutron gets shielded. And that's exactly the language that would be used if you were doing these types of calculations. It is like a shielding effect, yes. All right, so now we're going to go on to our simplified halo model, which I also know some of you will not be happy with, but but guess what? This is what we do. And we can interpret using any model that you want to give us. But essentially, what most experiments do is they use a standard halo model in order to plug into that master formula we've been developing in order to be able to compare results. And maybe once we have a detection, we can start getting into the nitty gritty if direct detection can help in any way say something about the structure of the dark matter in the galaxy. But the assumptions that we are going to make is that WIMPs are distributed in an isothermal spherical halo with a Gaussian velocity distribution. So this distribution, this F that have been lingering around in our formulas, is going to be equal to 1 over 2 pi sigma E E to the negative V squared over 2 sigma. So sigma here is a speed distribution, the speed dispersion, and it's related to the circular velocity by this factor. So sigma is the square root of 3 over 2, and the circular speed is 220 kilometers per second. And this is a number we've already used in some of our calculations, right? Okay, so we're kind of familiar with it. The density profile of the sphere, and so this goes back to your question about density, is proportional to r to the minus 2, and r naught, which is sort of our local dark matter distribution, our density distribution, we take to be 0.3 GeV per c squared. Although if you look, I mean, these are measurements that are done by astronomers, and you could kind of at any time find measurements out there in the literature between 0.3 and 0.4 GeV per c squared. Particles with speed that are greater than the escape speed. So this was the question about how fast can they go? This is the escape speed. Once you go higher than that speed, which is 650 kilometers per second, the dark matter particle is not gravitationally bound. So essentially the speed distribution is truncated at that value. And so this is something I like to do. Oh, sorry, you had a question or not? Oh, no, okay, I thought I saw your hand go like this. This is something, so this is a picture actually of my group last year, like the day before SMU shut down for the pandemic. And so you can see, here's Ashwita, who's right here in the front row. And this is Jasmine, who is gonna watch this video later online because it's like 2 a.m. for her. and then she's on video at this day, but yeah, literally the last day we could be in person at SMU. So I like to do this kind of calculation with students because I think it sort of brings it back to reality. Like, okay, what does this mean for me sitting in my room? Okay, so here we are in our work area, and we want to think about what the density of WIMPs means. So we know that the local density, let's just call it 0.3 GeV. So you can pick your favorite mass of dark matter particle. And so some of you might like a lighter dark matter particle, like say 0.5 GeV per c squared. Some of you might like a heavier particle, more traditional 60 GeV WIMP. And then it's just a very simple calculation to say what is the number density then in your area. So you can take this mass and you can transpose it into a number density just using some unit conversions. So that gives you about 60,000 particles per cubic meter for a 5 GeV WIMP. And it gives you about 5,000 particles per meter cubed for a 60 GeV WIMP, if I did my algebra right and my unit conversions. Okay, so then you can ask, okay, so that's per meter cube, which still, you know, for Americans can be a hard volume to think about. So let's transpose this into a 2-liter bottle of soda. So then we need to go to Google. If we don't remember, that 1 liter is equal to 0.001 meters cubed. And then we can do some simple unit conversions again to find out that a 2-liter bottle of soda would have about 120 particles if our WIMP was 5 GeV, and about 10 particles if it was 60 GeV. Now here, obviously, I'm not worried about the motion of it. I'm just kind of taking a snapshot in time and saying, what do we see? And so, you know, this is something that seems like we should be able to detect. Okay, so I think I just showed you a simple picture of how wonderful it is. Our dark matter particles are going to come in, they're going to interact via spin independent or spin dependent, our WIMPs are, and everything is going to be wonderful. Kumbaya, we build a detector. All right, but thanks to those clever theorists out there, perhaps it really isn't that simple. And Johan is going to talk about this in week 4. Maybe it is that we need to do something more sophisticated. And so effective field theories consider leading order and next to leading order operators that can occur in your effective Lagrangian describing the WIMP nucleus interactions. So maybe things are a bit more complicated. Okay, so I'm not going to go into detail about this, but I'm going to show you a few highlights just to give you an idea of how complicated it can be. And then I'm going to leave it to week 4 for the details. But basically, the effective field theory for dark matter contains 14 operators that rely on a range of nuclear particles or nuclear properties that are in addition to our spin independent and spin dependent cases. So they combine cases such that the WIMP nucleon cross-section essentially depends on 6 nuclear response functions. One of those response functions is spin independent, so case that we've talked about. 2 of them are spin dependent, and 3 of them are velocity dependent. So 2 pairs of these interfere, and then that would result, so if you have 2 pairs of these that interfere, you get a result that is 8 independent parameters that can also be probed. And so here are 4 papers that can give you lots of details about these calculations if you're very interested. And again, week 4 you'll get some. But let me show you here. These are the operators. Yes.
Just a general question. I maybe should know this, but what are nuclear response functions?
these are the nuclear response functions.
Got it. Thank
So
you.
it's basically a function that describes like how the response of the nucleus to the interaction is going to happen. These are they. These are 14 of them. And so, yeah, so these are the 14 operators. So just to kind of give you an idea of the parameters that are involved here without going into any detail on this stuff. So V perpendicular here is the relative velocity between the incoming WIMP and the nucleon. Q is the momentum transfer like we've been doing. S sub x and S sub n are the WIMP and nucleon spins. In addition to these operators, like just these 14, notice operator 2 is missing, but and that's because that's something that arises in a non-relativistic case. And since our WIMP, it can't arise in the non-relativistic case, and our WIMP is non-relativistic, so we don't consider it. And I see your hand there. So I just wanted to point out too that in addition, each of these operators can independently couple to either protons or neutrons. So even this gets more complicated than it looks.
So these are not operators, but these are the width coefficients which are attached to the operators, right?
I have to say, I have to claim ignorance. I don't know. I am.
These are operators.
It's operator.
I think they're the operators, but
I mean, again, where are the fields? It looks like it's the width coefficient. Oh, but you put these in like in the middle of dry cat,
yeah.
and the coefficient constructed to call this a coefficient.
These are non-relativistic operators. I think Joachim brought were
Yeah,
there's a few steps that will be.
Yeah, Yogi, I mean, I am not going to give a lecture on effective field theories. Sorry, go ahead.
Yeah, so one chi, one n, one chi is a numbering operator about how many parameters which is with the function, and one n will count the number of those.
Okay, so these operators do not appear really as they look like in the Lagrangian because the fields are missing. I was just thinking.
Well, there. Okay, so this is already
projected or
no projected. So since this is non-relativistic first quantized theory, that's basically the
okay, we're still in.
They are Galilean by
no, this is I don't want to go through the whole steps. So you
Yeah.
probably just to clarify. Now, so right now you're way down. You
Yeah.
cannot produce an anti-nucleus. So first quantized, that's the quantum mechanical version. You can rewrite this in a more formal language where positive connect with the quantum flow level. And hopefully we'll know about this week 4, but I think right now it's just flashing.
Yes, okay. This is an advertisement of this is going to come. Somebody who really understands this theory will talk to you in week 4. I knew there was going to be a danger, especially walking into a room of theorists, flashing this up, where people in the audience know more than I do. You know, be that a lesson, maybe, but the reason that this is important is to recognize that there's always something out there we don't understand, and it's important to talk about it just because you don't understand it, and because this has implications. And I want to show what these implications are for direct detection and tie it to direct detection, because these are things we think about as experimentalists as we're designing our experiments. So it's important at that level. I apologize that I cannot go into more detail about these theories, and that is not really my field of expertise. But definitely in week 4, you're going to get a lot more details about them, and I'm sure you will see these operators again. Okay, so let me say, so now if I kind of take a case, so the nuclear responses for different target elements vary. And so here are pictures for sort of 2 different operators. Let me just pull this out here. Okay, so so here are sort of 2 examples that illustrate the differences of the 08 and 09 constructive interference vectors, and basically for 4 different targets: silicon, germanium, xenon, and fluorine. And so you can see here that the results are, so this is essentially the event rate versus the nuclear recoil energy for these different operators, if you were to consider them. And what you can see is that the results give different rates between different targets, right? So different ones are favorable, and different spectral shapes. So look up here what the fluorine is doing. Okay, so what this tells us is, and the reason that I wanted to bring up effective field theory at all, is that it's really important that if you're going to have a robust dark matter detection program, that you need to have different materials. That this is going to be essential if it ever is that we discover dark matter and we want to start understanding better how those interactions are happening, at the nuclear level. We need different targets to be able to sort out which operators are the most important. And the spin independent and spin dependent cases, they're like the simplest cases that we think about, and that's why we started with them. But it's not necessarily, going to be the answer. Okay, great. So I think I have a, as I say, I think I have a good stopping point in a few more slides. So the message is here. So now we're going back to just our simple spin independent model again, and we'll be working with that for the rest of this course. The idea is basically you have elastic scattering of WIMPs depositing small amounts of energy into a recoiling nucleus, and we've seen that recoiling nucleus energy that we're depositing is on the order of tens of keV. Okay, and this is sort of a rate, and this is in counts per 10 kilograms of target material per year versus the threshold of your detector. For a dark matter particle, for a WIMP that has a mass of 100 GeV, and where the cross section between your dark matter particle and your nucleus is 10 to the minus 45 centimeters squared. Okay, so you can make this plot for any WIMP mass and any cross section you wanted. But you can see what you get in different target materials. So you can say, so essentially, if I have a threshold of 10, so I'm measuring 10 keV of deposited nuclear recoil energy. That means in, say, germanium and xenon, I will see one event in 10 kilograms of material in a year. And then, you can take a look and pick this up. So just to give you, to think about the challenges that we're talking about, why we need big masses. The other thing to note about this is like the spectrum is featureless. There are no knees, there are no breaks, there are no kinks that can help us identify what's going on. The event rate, very, very low, as I just illustrated. And at one event per keV for 10 kilograms per year, that means that the radioactive backgrounds of most materials are much higher than the event rate. So I have a whole series of slides talking about how it is that we have to think about materials and the lengths we go to try to characterize those materials. So we need large exposures, so that's mass times time, and we need stable detectors, right? Your detector can't be going down or changing its calibration every couple of days, makes it hard. Now that's for a 60 GeV WIMP. If you want to go lower, you're thinking about 10 GeV or 5 GeV WIMP, these lower WIMP rates, it gets even worse. Okay, so this here is a picture, the same setup before. In this case, we have a 5 GeV WIMP. Okay, here is our event rate per kilogram year versus our threshold. This is not good, right? This is hard. This is for germanium, so kind of just illustrating it one more time in another way for you. So if I have a germanium detector, so this is my event rate per kilogram year versus the threshold for a WIMP that's of mass 3, 4, 5, 6, 7, 8, 9, 10 GeV. Just to give you an idea of the type of thing that you're looking at. The reason that these numbers are bigger on this axis versus the previous slide is because the interaction, the sigma here, was thought to be 10 times 10 to the minus 42. Because if you ever look at our detector, like where our exclusion limit curves for lighter mass dark matter, we're not as sensitive to where we are in cross section yet as we are at higher masses. So this was to kind of give a picture of a snapshot of where we are, and if we can kind of make the next leap, you know, what are we looking at? So yeah, it's challenging. And so I think this is where, oh, actually, I have 2 more slides I want to show that are just kind of fun. And I think that will be a great place to end, but yeah.
So what is this threshold is a threshold, this threshold is a function of how you reconstruct.
This is the threshold of what you can measure in your detector. So like detectors, like the threshold of like, what is the lowest deposited recoiling energy that I can measure in my detector? So like, because detectors are built and they're made out of materials and humans that, you know, we can only do so much. So if you can get your detector to measure 2 keV of energy and reliably then reconstruct it and stuff, then yes, this is what you get. So it has to be based on what you have to, like this here is not a real detector. This is just a calculation of the rates. If I wanted to measure this, I would have to be able to measure and reconstruct and reliably believe my energy threshold is what it is at these low energies in order to measure this.
Is this the x-axis? Is this the recoil energy?
Yes, yes, this is the recoil energy.
So it's not the electron equivalent energy.
All right. Let me, and we will, if you don't know what electron equivalent or nuclear recoil equivalent, we're gonna go through all of that in the next lecture or the one after that. But let me just, I know we're sort of over time, but I really like this. This is my last slide that's talking about event rates. So I think this is kind of a fun plot. So this is the expected WIMP spectrum. And essentially, if I integrate this here, this is about 1 event per kilogram per year. We were talking about sort of that range. This is from the American Journal for Physics. I don't know if everybody knows about this journal, but this is essentially a journal that publishes a lot of undergraduate research in the US. It's put out by, I think, the American Association of Physics Teachers. So what this group did is they used a high purity germanium counter to measure a banana, because a banana is radioactive, okay? So this is their spectrum without the banana. This is the spectrum with the banana. The blue is the difference. It's like 100 events per kilogram per year. And in our detectors, these would be electron recoils. So just to give you an idea of what a banana would do if we could put it in our detectors, I mean, it would be disastrous, right? I like this because a lot of times when I have undergraduates doing research, they do a lot of material characterization stuff with me. And they always have to like talk about it in front of the donors that sponsor their research and stuff. And so I always like to say, you know, a banana is radioactive. and I like this because it quantifies how radioactive your banana is. All right, so I think we'll end here. Next time, we're going to talk about the fact that all hope is not lost. It turns out that there are some experimental signatures that we might be able to measure from WIMPs. And then we're going to go into talking a little bit about background and then into experiments. And I'm pretty sure at this pace, we're probably going to have to steal a little bit of the discussion time tomorrow evening to finish up, if you would like. All right, thank you guys.
And next is also in person, right? It's crazy.
Yeah.
Yes.
So we leave it as it is.
We leave it as this, but this is my laptop.
But you stop the recording now?
I stopped there. So you restart the Zoom, I think.
Yes.
And then I'll record
Hi.
my. I have a question. Sorry.
Yeah.
I'm going to pieces so that the choice that you make